board. Okay, so yeah, welcome to today's lecture on thermal sensors. We'll continue with this chapter, and hopefully this week we'll finish. I will also bring my agenda tomorrow so that we can fix some examination dates. Yeah, as you know, I'm flexible, and we just fix some examination dates that suit you. And if those that are probably on the system already, defined, I don't know, by the Prüfungsamt, if those suit you, that's fine also. And I will come with the full information tomorrow. So let's have a look at agendas. And you probably know already when your other examinations will be, so that you can place your examination optimally in the examination period. Okay, so that's for tomorrow. For now, we're talking about thermal sensors, namely infrared sensors, and even more in particular about thermoelectric infrared sensors. And the example that I showed last week briefly was this 16 by 16 sensor array made of these 256 pixels. Each pixel receives infrared radiation through an optics, so that an infrared picture is taken from the environment, and whatever distribution of heat sources you may have out there is then reproduced on this low resolution sensor array. But it's maybe enough to detect that there is a person there with a hot head and two more in the front, and then another one here more in the background, and maybe even the guy in the back will be recorded. And then the system knows, oh, there are 5 persons in the room. Maybe we'll have to increase the ventilation a bit more to reduce the CO2 level. So this is a typical application of infrared scene detectors. And I think there was a rough picture of how this looks like with a very simple system with only 2 pixels, where only 2 segments of space are mapped, and therefore the presence in either of those sections of a heat source can be detected, or the motion of a heat source. And here the spatial resolution is of course much finer. And this detector can be called a bridge type detector, because this is like a bridge going from one support over a big abyss to another support. The bridge isn't straight because we need to, or it is a necessity to micro machine it using at that time wet anisotropic silicon etching. And the method we used here was EDP. There is also TMAH, water aqueous solution that can do the job. But if this was a straight bridge from one end to the other, then edge pits would form to the left and right, or the front and back of that bridge, and it would not be under etched. And because we have these corners, there is some under etching that can occur now. And therefore, the whole bridge is under etched, and actually the edge pits under etching each of those little bridges form one big groove, as I said, over which 16 bridges are suspended. And the silicon between these grooves can be used to contain some switching elements to address individual pixels in a system that was also realized. And so here's another example of an infrared sensor, also a chip of rather impressive size, 5 by 6 millimeters square, and it contains 10 by 10 such infrared radiation sensor pixels. You don't see any under etching here. There is no under etching. Each pixel is a membrane. And so the etching was done in this case, was done from the rear of the wafer using KOH, etching away all the silicon through the wafer until the silicon oxide on the front from the CMOS layer stack was reached. As we saw in chapter 2, you can do KOH etching, and there are some cross sections and everything, and that's the KOH etching that was applied here in a wafer box with some rinsing liquid in the front to prevent KOH from aggressing that front side. Yeah, and the membrane is, of course, a rather large membrane. It maybe has 3 by 3 millimeters here in size, which is sizable. And as we have also seen in chapter 2, those thin films are stressed. And so to have a large membrane of pre-stressed materials that would like maybe to expand because they are compressively pre-stressed could cause fracture. And so in order to prevent that, this whole membrane was stabilized by these white lines. You see these white lines? These white lines are these actually double lines of pretty thick gold. So 25 micron thick gold, maybe here, I would say 100 micrometer wide. And those, or 50 to 100, what is here is 100 micrometers, so 50 micrometer wide lines roughly. And those gold lines were produced using the gold electroplating process of the company, Microélectronique Marin, who allowed us to produce our sensor chip ideas on their process. And they had this gold bumping service, which is usually done for adding gold bumps to the pads, to the contact pads. And we have seen other examples where we misuse that gold to produce some structures of other utility. And here the usefulness is given by the mechanical stability of the gold on one hand to stabilize the membrane, and on the other hand by the fact that it's a superbly thermally conducting material. So if the chip is at temperature T0, all along those gold lines we have, and T0 also here, all along those gold lines, we have temperature T0. So this is kind of the reference temperature. And if now a surrounding, every pixel, so the pixel is suspended on those the square shape of gold lines, and so it has temperature T0 at its edges. But if infrared radiation impinges on the pixel, it heats up the center to some temperature T0 plus delta T, and that plus delta T allows then to make a measurement of this delta T proportional to the incoming radiation. I should maybe say to the flux of the incoming radiation. And that increase can be measured again by thermocouples. Some material 1 connected to some material 2. Let's make it yellow to see it really nicely, and then back to blue material. So back and forth many times, and those form a thermopile, and then the thermopile is also on the other side. And so we have 2 thermopiles that are connected in series, and those produce a voltage proportional, a delta V output, or delta V out is proportional to delta T, namely N, the number of thermocouples times the Seebeck coefficient of those thermocouples times delta T. And so what was used here, so this was a single poly double metal process. So what thermopiles could one make? Polysilicon against metal. Aluminum, double metal in that CMOS process meant some aluminum alloy, and the pixels themselves are 250 micrometer large. The pitch is 330. So from here to here, we have 250. And then let's say from some point to some other equivalent point, it's 330 micrometers, and that 10 times. And so my early estimate of that membrane, 3 millimeters square, was not too bad actually. And so so this, how many we have 12 thermocouples, 12 thermal N plus polysilicon metal thermocouples in this picture. Hard to see. It's kind of stripy, and you don't really know what it is. So there is some finite resolution. If I look here, maybe do I see something? No, I don't see either. So you have to take my word for it. There are 12 polysilicon metal 1 thermocouples, 6 on each side, and the poly is 30 micrometer wide, and the metal is 1.5 micrometer wide. The polysilicon is much wider than the metal because the metal contributes little to the thermoelectric effects. Aluminum is not such a good thermoelectric material, so there's no reason to waste space for it. And why then the polysilicon to make it large? Well, it's a resistive material, much more resistive than aluminum. So in order for this whole sensor to have a resistance, our pixel to be as small as possible, it's good to invest as much space for the polysilicon and little space for the aluminum. And furthermore, the aluminum is also a very good thermal conductor. So whatever heat comes here, let me call this heat power. The heat power deposited in this pixel is then causes this delta T via heat conductance. The power H is related to delta T via the thermal conductance or heat conductance, and that heat conductance consists to a large part of aluminum if the aluminum is wide. So making this aluminum small, narrow, makes a lot of sense. Just to remind you, the kappa, the thermal conductivity of aluminum, is around 240 watt per meter and Kelvin, and the kappa of polysilicon, so polysilicon, is let's say somewhere between, depending on the material, between 20 and 30 watt per meter and Kelvin, roughly a factor of 10 smaller. So making the aluminum as small as possible makes the thermal resistance larger, or the thermal conductance smaller, so that delta T can be larger for a given heating power. So that's all consistent. And now, based on the pixel resistance, you would now be able to determine the noise caused by that pixel. There was this noise formula, square root of 4 kBTR times delta F. So for a range of frequencies, let's say 1,000 hertz, to have millisecond thermal resolution, that would then make a noise of 4 nanovolt for a kilo times 4. So let's look at those numbers. It was 4 nanovolts for a kilo ohm resistor for a square root hertz. See, where is that? Yeah, 4. So for delta F1 hertz and 1 kilo ohm, we had 4. For 1,000 hertz, that would be multiplied by square root of 30, and square root of 1,000 times roughly 31 point something. Okay, that is then already 100 nanovolts, and that is the noise that comes out of the pixel for 1 kilo ohm, and then we have to multiply it by square root of 3.6. So another factor. So quite a bit of a fraction of a microvolt of noise voltage coming out of that pixel. And so the thermoelectric voltage generated by the incoming radiation needs to be at least as large as that fraction of a microvolt. So the noise equivalent power must come in so that at least one has a chance to detect a signal with signal to noise ratio of 1. And so these are the considerations that the designer of this sensor, in particular here, Nikolaus Schneeberger, had to go through. And then one should not forget that this pixel is also connected to some circuitry, and the circuitry adds noise. So there is no circuitry, some magic microelectronic circuitry that can remove noise. Microelectronic circuitry generates noise, and it may amplify some signal with some noise, but then it amplifies the signal part of the signal, but also the noise part, and it adds its own noise. And so this is an important criterion. So here's a schematic description of the circuitry that was implemented in that system. You may have had some microelectronic lecture, I don't know about that. Maybe it's no longer obligatory in the international masters. The German master students definitely have had some microelectronic lecture by Professor Manoli or Dr. Keller. And so here, this is a so-called fully differential 3-stage chopper amplifier. So there comes the signal, and then it is chopped with a frequency larger than the flicker noise cutoff frequency. So now that's again circuit design. These microelectronic circuits contain field effect transistors, and field effect transistors generate noise. So microelectronic circuits always have noise. And that flicker noise, that noise related with the field oxide and the motion of inversion carriers close to the silicon oxide, causes a noise that is 1 over F. So if I say flicker noise, it's 1 over F noise. At low frequency, we have a lot of noise, and then it goes down at higher frequency. And then at some point, there is a thermal noise floor that cannot be overcome. I mean, it's there because the lattice vibrates and so on, has a temperature, and the carriers have to follow that temperature. And then there is this cutoff frequency, and then it would be ideal to make all measurements at frequencies above that cutoff, because then you're on the noise floor, the minimum noise that for sure cannot be overcome. And so how do people do that? If they have a signal that is in this lower frequency range where flicker noise is important, they just chop it, and by chopping it, they produce a signal that is then at higher frequency, because the chopped signal consists of, well, sinusoidal terms that are above maybe that frequency corner if that chopping frequency is high enough. There's the fundamental, the first harmonic, second harmonic, and so on. And those signals are then out of range of the flicker noise. And then one can do some microelectronic measurements there, amplification, blah, blah, blah. And then one takes what one has and multiplies it back or deconvolves it by the inverse operation of that chopping, and one extracts the amplitude basically of the signal, and that is a measure of what came in here as the DC part of the signal. And so this is done here in 3 stages. Now, of course, you need an oscillator that allows this chopping to happen. You have a first preamplifier, then there was a band pass filter with different band pass width, which is indicated schematically here. That's also an amplifier with a gain from 10 to 25, here a gain 5 to 20, and the third stage had another gain of 20. So the microvolts, or fractions of microvolts, were boosted into a decent range, and out comes the signal. And so I'm not a circuit specialist. I can only think what Professor Manoli would think of this. So this was designed by Christoph Menolfi at ETH Zurich under the supervision of Professor Chuting Huang. And he was a specialist of chopper amplifiers. Professor Manoli, who taught microelectronics until recently, or Dr. Keller, and now Professor Kuhl, they are more in sigma delta or delta sigma amplifiers, another technique that also does things like shifting the spectrum out of the way and then doing noise shaping and so on, and then using that signal. So there are different techniques, and this chip was operated at 5 volts. It has a huge DC gains or good amplification. It also had a common mode rejection ratio. So what does that mean? You have actually a fully differential design. So there are 2 inputs from a sensor and a reference, and then it's the difference of two signals that is gained, and if those move up and down in parallel, yeah, and that doesn't influence the measurement, that is the common mode rejection. And then there is a common mode rejection ratio that computer microelectronic circuit designers like to do, and there is a noise, 8.5 nanovolts per square root hertz. It has no flicker noise, of course not, because of the flicker of the chopper technique. Different gains can be set depending on those parameters here. The bandwidth can be set, and then this whole chip is quite large, 3 by 2 square millimeters. Meanwhile, Niklaus Schneeberger characterized his pixels individually, and he determined their resistance to be quite homogeneous, these 3.6 kilo ohm that I mentioned before, and the responsivities with certainly some errors that I would request nowadays of my students, some error bar, they are also kind of homogeneous, and I don't know now how reproducible these numbers are. That would have to be determined, but I guess that what we see here is mostly noise of the measurement. So a responsivity or sensitivity of 4 volts per watt. You can imagine that when 1 watt of radiation power impinges on the pixel, it produces 4 volts of output signal. Of course, there is not 1 watt, there is microwatt coming in, so that microvolts of signals are coming out. And those microwatts that come in correspond to a certain temperature of the object being projected onto that pixel. So there's a noise equivalent temperature difference that can be detected, and it was a few degrees for that system. There are other groups who have worked and who are still working some on those thermoelectric infrared radiation sensors. So one group that is very famous that has also appeared in other contexts in chapter 2, for instance, the University of Michigan at Ann Arbor, very famous university, one of the top universities in the United States. And in the group of Ken Wise, there was Dr. Oliver's group who produced a 32 by 32 sensor array. They call it focal plane array. That is also a name that is given to this kind of structures, focal plane array, because that plane array is put in the focus, the focal distance of some projecting system that maps the environment onto them. So that focal plane array. It was done in a 3-micron CMOS technology that they had available at their labs there. They did EDP etching, obviously from the back. It was a big membrane with many pixels schematically shown here as a series of 3 pixels separated by some silicon. So there are silicon beams underneath the membrane, like the gold beams on top of our membranes. And those structures were etched by some tricky EDP etching from the back. That's what they like to do. And that left some silicon, left some silicon, because certainly the etch mask was not an opening like here, from here to here. This would have generated a full array, but there were some other structures that probably led to some. So let me just schematically sketch some additional mask structures on the back of the original wafer. On the initial rear that allowed, some more complicated silicon remnant structures to be left over, which is some design that you have to understand and to do. And so in these silicon ridges, you see also some components, and it says switch. Yeah, so silicon can of course carry some microelectronics, and the switches to address these individual thermopiles in order to read out individual thermopiles from these individual membranes were integrated in that silicon infrastructure. 370 by 370 micrometer large pixels with 32 P polysilicon, N polysilicon thermocouples. Leading to a larger responsivity of 15 volts per watt, because there are, first of all, 32 thermocouples per thermopile, and then they're not polysilicon against aluminum, but against N polysilicon, and the Seebeck coefficient of these two materials have opposite sign. So the alpha of P poly slash N poly. So if we have here some 100, let's say 200 microvolts per Kelvin, and here we have minus 200 microvolts per Kelvin for the individual material against aluminum. This will then add up to something like 400 microvolts per Kelvin. Whereas P poly or P alpha P poly against aluminum is just this, and this is alpha N poly against aluminum is equal to this thing here. So we have a more substantial output. So this explains this larger responsivity, and then the detectivity of the sensor was 1.6 times 10 to the 7 centimeter square root hertz per watt. And we can compare that with other numbers quoted earlier to see that, thermoelectric sensors are not as good as pyroelectric sensors. Then what else do we have here? Some work of Nissan. A bit later, a larger focal plane array. Oh, that's already quite some resolution. A custom 0.8 micron CMOS process. A special processes added front-end bulk micromachining. So they did some micromachining at the beginning of the CMOS. Okay, let me not talk about that in detail. Some vacuum packaging. Of course, vacuum packaging helps. If the heat that is absorbed here and leads to some temperature T0 plus delta T in comparison with the substrate temperature T0, if this heat power coming in through radiation is not lost via conduction, P conduction through air, because there is no air, there is vacuum, or from here, conduction, P conduction to the nearby boundary condition of T0, or here, P con. If those channels are removed, then of course the delta T will be higher. And so that is the purpose of this vacuum packaging. And then they also added some gold black absorbing layer, some very thin gold layer. Gold isn't black, is it? Black gold we don't see so often. It's usually shiny, even and you can hardly get it dirty because it nothing sticks to it, so really it doesn't oxidize. And so what is black gold? Black gold is a sufficiently thin layer in which infrared radiation of the wavelength that is being measured here, 10 micrometers, does some internal reflection, and then there is optimal absorption. So it's kind of a Fabry-Perot filter for infrared radiation, and because of the somehow the refractive index or so, it makes it happen that actually that material absorbs infrared radiation very well, and that is called black gold. And for every conductor, there is a thickness that makes it optimally absorbing for infrared radiation. Yeah, what else do we see here? Two pairs of N-poly-P polythermocouples, 100 by 100 square micrometers. And so after amplification by 2000, there is a responsivity or sensitivity of 3,900. So the output of those thermal piles is 1.95 volts per watt. Okay. And my friend Tayfun Akin at Middle East Technical University in Ankara produced also some thermal pile-based sensors. We'll see more from his type of research, with a decent responsivity, decent size, and well, rather decent detectivity. So this was all on the thermoelectric sensors for infrared radiation. Now let's look at some bolometric infrared radiation detectors. So you can also make bolometric focal plane arrays, pixel arrays to which infrared radiation scenes are projected. And those pixels now look different. They are absorption structures like this little suspended plate, which is suspended on two legs. So here's an anchor, here's another anchor, and then there is a little arm that leads to this slightly elevated absorption pixel. And here is the other arm that leads down again to the second anchor. And again, the principle is the same. I mean, the principle was shown much earlier. Let me just check whether we find that picture again. Yeah. The principle is always this structure. You have an absorber for radiation power, h nu, or the pH that comes in, is absorbed. And then the temperature is increased because there is a thermal resistance of that absorber with respect to its environment. And that temperature needs to be measured. And so the measurement is now in the bolometers is done not with thermoelectric structures, but with a resistor. So you have basically a line of resistive material that meanders through this structure. And now you can measure the resistance between this location and that location. So what will happen schematically? A current. No, that's not the symbol for a current source. What is a current source? Is that something like this? You're the electrical engineers. Does one draw a current source with this ball, the bar? So current is sent through this structure. And then at the same time, a voltage is measured. I'll indicate that like that. A voltage is measured, and from that you obtain the resistance between this point and that point. And that resistance is dependent on temperature. R of T is equal to R0 times 1 plus a temperature coefficient of resistance, TCR, beta, as it is sometimes called, or it's also called alpha, by some. I'll call it beta, and times delta T. So the resistance, this is the resistance at temperature T0, this R0. The resistance is changed because there is a delta T. And if you can measure that resistance change by comparing that changed resistor with another resistor that doesn't change, for instance, in a half bridge or in a full Wheatstone bridge, then you have an indication of delta T, and that indication of delta T, temperature increase over the temperature of out here of the surrounding chip, that delta T is an indication of the power, the radiation power that comes in here. Yeah, and so this has been this structure has been presented by Cole and co-authors. They were from Honeywell. Honeywell was in the 90s a company that was very, very aggressive in developing MEMS for all kinds of applications. They had micro-machined gas flow sensors, micro-machined infrared sensors. They still do that. Micro-machined gas flow sensors actually by Honeywell are, were not so good. And that was found out or analyzed by Felix Meyer, PhD student in the group at ETH Zurich, which I worked in, and he thought, those sensors of Honeywell, they're really bad. I can do much better. My sensors are much better. They have a much better potential. And he had reasons to believe so. And so ultimately he founded company Sensirion based on his own structures. But Honeywell was very broadly, and they had developing MEMS, and this sensor here, this bolometric sensor is excellent. And so how does that work? First of all, it's integrated on a CMOS substrate. You have these lines, these are parts of a CMOS, underlying CMOS microelectronic circuit on which the structure is built on top. So this is a post-CMOS fabrication process. The microelectronics is produced, and then some sacrificial layer is deposited, some other materials are deposited, and dielectrics to insulate, some meandering line is structured, and then at the end, the whole thing is micro-machined, and then you have your bolometric array. And what circuitry is below? It's an addressing circuit that allows to switch on or off an individual pixel. And so interestingly, what Honeywell did was to use their structures in two ways. So one way was to send a current through that is large enough to heat up the pixel. So you could have a scene of pixels on the chip that produce different temperature deltas because of internal heating. One pixel gets hotter, another pixel gets cooler, depending on some pattern that should be generated. And that was used with some optics to generate some thermal scenes, so that a detector system could be confronted with a thermal scene that is technically well defined. You don't have to move by some big things in the back. The thermal scene generator was a microsystem. And then the same system could be used as a thermal radiation detector, where indeed an external radiation comes in to be detected, and then you need to switch on one pixel after the other to determine what its own delta T, or I can also write this as R0 plus delta R. So R0 times beta R times delta T is, of course, delta R, its own delta, not delta R0, apologize. So delta R. So to determine what its own delta R and therefore its own delta T is, and therefore its own heating power, and therefore the temperature of the object out there at its location, its corresponding location. And this is done with some simple logic where the resistance measurement can be switched on and off by some integrated transistor in the subjacent infrastructure, and by having some address and column, address row, some address row and column. And if this transistor is switced on among all the pixels that are now on that same, hooked up to that same line, then they will all be switched on, but only the pixel on at this location receives a column signal of, let's say, a volt to let a current fly through flow through so that its resistance can be measured. So having the column address and row address active then lets one read out that particular resistance, and therefore the thermal information that generates the signal at this pixel. And then the next, pixel per pixel is read out. And maybe this is done in parallel by parallel systems so that the frame rate can be larger. And then you measure a thermal scene at one moment, and then at the next moment, at the third moment, etc. And you have a thermal video of your environment. So this is how these pixels work. And now let's also look at the size. So here we have 50 micrometers, so that's much smaller than the thermoelectric structures. And you also see some interesting feature, namely that this absorber has only a very weak mechanical link and weak thermal link, therefore, to the chip below. So the thermal conductance of between the absorber and the reference structure below will be small. And therefore, for a given input power, the delta T will be large. So the sensitivity of these structures are potentially larger because of their inherent construction that allows us to make them not so well connected to the thermal surrounding world. So here's are some pictures of different structures that you see here. Oh, for instance, this is a structure from one of the pictures in this paper where indeed a meandering resistor goes through from one connection port to another connection port or anchor, and then there is this gap, hopefully vacuum, and another structure viewed from the top looks like this. So let me draw that here. We have this anchor point, and then a line, a little beam going up to here, and here the second anchor point with the other line, the other suspension going up the hill to this pixel in the center. Let me draw that pixel maybe in color. So this is basically the absorption structure here. Of course, this line is also sitting on some material, a little beam of material, but the absorber is here separated from the beam by a gap. And now this little conducting line connects at this location. Here is a contact to a third material here as well. A third material that is integrated in this absorbing pixel, and let me draw that in green, a structure that looks kind of like this. This is a special material, namely vanadium oxide. Hard to read. Let me write that in yellow. Vanadium, let me write it as vanadium oxide. Actually, VO2 is a fair approximation. And ideally it would be VO2. And vanadium oxide is a material. Well, let me write that down. Oxide, VO2, has a beta of resistance of something like 3% per Kelvin or degree centigrade. That means if you change its temperature by a degree, its resistance changes by 3%. That's huge. Usual metals, if I draw a resistance of a usual metal like platinum, gold, aluminum, simple metals, as a function of T, what will I see? I will see a curve that is essentially linear. Small deviations are possible, but let's say the first look will say, oh, this is quite linear. And it goes almost through absolute zero at zero. So maybe some deviation. But it means that, for instance, at 300 Kelvin, if this is really according to a linear curve, if you change the resistance by, or the temperature by 1 Kelvin, the change in resistance will be 1/300th of the resistance value at 300 Kelvin. If this is now the 3R, then here we have R at 300 plus 1 Kelvin, and that is equal to R0 plus R0 times beta R times delta T, which is 1 Kelvin. And that implies that this beta R at this temperature is about 0.3% per Kelvin. 1/300th. 1/300th is 3 parts per thousand, roughly. 0.3%. This is a factor of 10 larger. And the reason is that this is not just a normal metal, it's an oxide that expands, that has a thermal property, that the band gap, it's almost an insulator. It's not really a semiconductor. It's more conductive than a semiconductor, but it's at the brink of becoming a semiconductor, and that makes a huge temperature coefficient of resistance. Actually, the phenomenon that occurs here is that of a so-called Mott transition. The transition of some materials to transit from conductive to insulating or semiconducting first properties with a band gap. And so this is the principle, and this vanadium oxide is here just one thin layer. It is not so conductive. So if you would like to make a measurement, it is good to have a few tens or hundreds of ohms. With vanadium oxide, this is possible in the form of a single piece of material. If you have something more conductive, like maybe this platinum line, if it's a platinum line, then you make a meander in order to accumulate more resistance to make the measurement easier. And then, well, there are some other designs of such structures. You see here some absorbers that are suspended on 4 locations. Probably 2 are used again to make some resistive measurement. Here you see a close-up of one of those or one of those thermal sensors. So here a little post actually, and then a planar structure produced by some sacrificial micromachining. So if I show you the process here, and that's again from Cole. This first example that I showed, you have here a silicon chip that has been completed in its CMOS fabrication with a planar surface. There is a passivation layer, and then some sacrificial polymer is deposited. Before that, actually, a little reflector, a metal reflector, maybe platinum or gold, with a sheet resistance of 360 ohm per square is deposited. And that makes it now not an ideal absorber, black gold, so to speak. It makes it ideally white gold. It reflects the radiation optimally. And then comes the sacrificial layer, which is spun on and then etched, and then the passivation layer. This is the passivation. The passivation layer is also opened to reach some contact pad to some subjacent circuitry or subjacent metal lines. And then there is a thin silicon nitride that is deposited by chemical vapor deposition all over the place and into these little holes. And then there's a first metal and the second metal. They don't talk in detail, but this could be this vanadium oxide resistor material. And then the whole thing is covered again by silicon nitride to protect that resistive material. And then the structure is structured with an additional photoresist into the structure that we see, where the silicon nitrides need to be opened to produce these beam structures, and then the absorber structure and the other beam structure. And then this beam is suspended. Actually, this suspension looks very much, very much like this suspension here, this anchor point with a vertical post, and then the rest a planar deposition. Whereas the structure that you see here schematically doesn't represent that truth ideally. It looks like it comes from the bottom and then goes somehow up. I'm not sure whether this was intended here. Maybe it's just badly drawn. And actually, this is some suspension on a post. The line inclination, it's maybe just by accident badly drawn, and this too is also flat. So if they are flat, then this cross section corresponds to what should be shown in that schematic. And so what you see here is this absorber on its support, and then the absorber contains within its thin film sandwich of silicon nitrides the metallic conductor, which in some cases of Honeywell is this VO2 resistor. And so this has a resistance of 20 kilo ohms per square at 25 degrees centigrade. And if we look at this, it almost looks like a square. Maybe it's a little bit wider than long. So this may be actually half a square effectively. So the resistance of this object might, be estimated to be somewhat below 25 kilo ohm, maybe 15 or so kilo ohm. And the temperature coefficient of resistance is actually -3%, not +3%. Yeah, so I just wanted to give an order of magnitude. I just said the positive number. And those distances here, those are a few micrometers. So that's as thick as this sacrificial material is. And this distance here is roughly 50 micrometers, so quite small. And then you have these internal structures. And then about this reflector. So what is the purpose of this reflector? If infrared radiation comes in, so ideally it is absorbed in the absorber. But part of it is also going through. And if there is this reflector, it is reflected back and then gets a second chance of being absorbed. This is a simple way to boost the sensitivity by giving the light a second chance to be absorbed. Solar cells use that a lot, actually. Solar cells have the sunlight that comes in and that crosses the sensitive material, the PN junction, and then it's at the back. And if it went out, we wouldn't have the efficiency that we now have, so 20% or more. The back is also metallized so that the light can move back through the silicon a second time. And then you may know that the top surface of silicon solar cells is structured. It's etched like little inverse pyramids. And then the light that is coupled through gets a chance to cross the silicon for a long time, and then a second time for a long time, and then it would get out again maybe, but because there is some inclined wall, it is reflected back and forth many times, and then you get another % of efficiency out of the material. All right. Yeah, so I took some numbers from that paper and thought it would be interesting to talk about those numbers. because they illustrate many interesting aspects of these sensors. So let me see if I have those notes again. I went through some calculations. Yeah, so this structure, first of all, it is operated in vacuum, or in vacuo, as some people who insist on Latin being Latin say. So that there is no thermal conduction. The thermal conduction loss P cond through air should be excluded because the distance is so small that if this is filled with air, then you have delta T divided by a small distance times a kappa of air, a few micrometers, in the continuum regime of the conduction. This is at Knudsen numbers much smaller than 1. Then you have kappa of air 0.026 watt per meter in Kelvin times delta T divided by a few micrometer. Oh, that removes that heat really efficiently. And you would like to benefit of the fact that there is, well, some P conduction through those arms. Of course, the same here. P conduction through arms, and only that. Well, only that. At least not the conduction through the air. And then you are still facing, in addition to P radiation loss, because this is a gray body of some epsilon that loses its energy also by radiation if it's heated up over the temperature of the environment. The delta T makes it happen. This formula of 4 or 8 times epsilon times T0 to the cube times delta T that we developed earlier comes to bear here. So eliminating, loss channels is important, and that means that this structure is operated in vacuum. And then the thermal conductance, that is the connection between the power that gets dissipated, the heat power that gets dissipated, and the delta T that it generates, this thermal conductance. Let me think. I times R, yeah, this is the thermal conductance. That thermal conductance should of course contain as small and as few terms as possible, and for that structure it has been calculated to be 10 to the minus 7 watt per Kelvin. So if a pixel, and one of those pixels here, with its suspension here, receives 10 to the minus 7 watt, the ensuing delta T will be 1 Kelvin. For 1 Kelvin, the power is going to be 10 to the minus 7 watt. 10 to minus 7 watt per Kelvin is GH, or G thermal, as it's called here. And then you can estimate that each of those pixels receives something like 10 to the minus 9 watt. Now that's a very small estimate, assuming some heat source out there 10 meters away, and then this pixel receiving some fraction of space from that source over that distance. That object is maybe 10 degrees above ambient, and that means the chip temperature. And so you can estimate the power that this black body radiates into space and how much of it finally ends up on those 50 by 50 square micrometers of area. That's not a lot. Although that body maybe radiates with 100 watt, it's 10 to the minus 9 watt, roughly, that could end up on that pixel. And that means that if this power being absorbed is also the power that is now conducted away in its attempt to produce some delta T. Well, if that is 10 to the minus 9 watt, then the delta T will be 10 to the minus 2 Kelvin. It means that this power produces a temperature increase of 10 millikelvin. That's not a lot. And these 10 millikelvins need to be measured. Now, the resistance, I said, okay, let's estimate it at 50 kilo ohm. Well, I put this number here. It's maybe only 15, as we just said before, or 10, or for other materials even less. I just assumed, let's assume 50 kilo ohms. Now, if we operate this structure at 5 volt, then the current that flows through the structure will be 2 times 10 to the minus 5 amp. And with a temperature coefficient of 3% per Kelvin, 0.03, 3% per Kelvin, 0.03 per Kelvin, that means that if the temperature, the resistance changes, the current will also change, and the relative resistance change will be equal to the relative current change. That's because R times I is equal to V. Actually, should be a minus, honestly. There must be a minus, frankly, because if this changes by 1%, this has to, so if this is increased by 1%, I has to decrease by 1%. If this changes by 3%, then this has to decrease by 3%. But anyway, the absolute values of the relative current change and of the relative resistance change correspond to each other. And that can easily be calculated now for this temperature change with this temperature coefficient of resistance. It means that the relative resistance change and also the relative current change that flows through the resistor is 3 times 10 to the minus 4. That's a small relative change. And now the current flows, which is 2 times 10 to the minus 5 amp, which means that the delta I that we will have to detect corresponding to these 10 millikelvin will be 6 times 10 to the minus 9 ampere. So the circuitry has to be quite performing. We have a baseline of 2 times 10 to the minus 5, and now there's this tiny change that needs to be detected. So the next question is, can this be detected at all? Because this resistor is also a noisy object. It's a noise source. It's a current noise source. So let me go back to these earlier slides. Do we have them? The noise slides. Yeah, we've had some formula. This one in particular. So if you measure the voltage of a resistor, it just stands out there without any other things. The charge carriers moving around will cause a voltage fluctuation. And that voltage fluctuation is described by this formula. Now the question is there something similar for the current? Some noise current. And that is the case. If you power a resistor with a given voltage, so if the voltage is given, and you measure the current that flows through that resistor, that is going to be, of course, you will say, the current is going to be V over R. But there will be also some I noise voltage, some stochastic noise current adding to that fixed value of current. This is given and this is given. Yeah, and this I and R is related to the V and R as any voltage and current are related, namely by V and R divided by R. And this is then square root of 4 kBT. And what did I write? KB, this needs to be large. 4 kBT, yeah, times delta F divided by R, all under the square root. And I'll make a big bar here so that this stops. No, it's basically this formula divided by R, and the R therefore comes under the denominator here, divided by R. So this is how you can calculate the noise current of a resistor exposed to a fixed voltage. And this is what we use here in this page. Where is it? Yeah. So this is exactly what I calculated here. Yeah, it's the noise voltage. And sorry, I need to go back to this square root hertz. Well, no, that's fine. Let me stay here. That means that this factor without the delta square under the square root in the formula on the previous slide, yeah, amounts to 5.6 times 10 to the minus 13 ampere per square root hertz. Yeah? If you multiply that with the square root of the frequency bandwidth, then you have the amp of noise voltage over that frequency band. And for 1 square root, for 1 hertz, yeah, this produces this kind of this noise. And now we have a frame rate. I said, okay, what is the frame rate? 14,000 hertz. Yeah, 70 microseconds of time per pixel, because there are so and so many pixels, and there are, scan through, and so that is the measurement time per pixel that corresponds to 14,000 hertz. So this is the bandwidth. The square root of 14,000 is multiplied with this number here, and that gives you root mean square noise of 6.6 times 10 to the minus 11 ampere. Yeah? And this is fortunately much smaller than the current change caused by the absorption of radiation leading to that temperature change. Yeah? So there is an electrical signal to noise ratio of 100. So there is a lot of space electrically for measuring that temperature change, thanks to that material with its large temperature coefficient and its reasonably low resistance. But this is not the only source of noise. Yeah? So let me draw that that pixel now as a little block of material. Yeah, and then we have here its suspension designated by T0, and it's thermally connected to, so here is T0 plus delta T. So it's thermally connected by a thermal resistance, yeah, which is equal to 1 over G thermal. We have that. And a thermal resistor lets heat flow. But heat is not something which is continuous either. It's like current is not a continuum. It's made of particles, of electrons that flow. Heat is also made of particles, namely phonons, of lattice vibrations that are quantized. And so there is a constant exchange of that thermal bath with this little thermal object of heat quanta going back and forth. And so the heat content of that object fluctuates, which means that its temperature also fluctuates. And that temperature fluctuation has something to do with its heat capacitance, C. The heat capacitance is equal to the volumetric heat capacity, specific heat capacity, multiplied by the volume of the object. And for this little pixel with its thickness of 2 micron and 50 by 50 micron in size approximately, I estimated something like 10 to the minus 9 joule per Kelvin. Yeah, so if 10 to the minus joule arrive from, arrive here of energy, the temperature change delta T will be 1 Kelvin. So that is one thing. But then the interesting thing is that because of that back and forth conduction, this quantized thermal conduction, there will be this thermal root mean square noise in temperature. And that is given by this square root, which looks kind of similar to another expression which we have seen, KBT over C, the square root. You have seen that on which page? Let me see. Was that here? Yes. Here we had an electrical formula that said that if a capacitor is at temperature T, over all frequencies that are relevant, this capacitor will have a fluctuating noise voltage given by KBT over the electrical capacity of that capacitor with the square root. The formula that you have just seen looks a little bit different. We have a C, which is now a thermal capacitance because we are talking about thermal capacity, but the C is divided by T. So let me go back to this formula here. C is divided by T. This is interesting because here we have joule per Kelvin. So this is heat per Kelvin, but the output which we measure is temperature, and the thermodynamically conjugate quantity conjugate to temperature is entropy, and entropy is heat per temperature. So this heat energy or thermal energy per temperature. And when we talk about changes of entropy, changes of entropy, it's like changes of temperature. And then this leads us to the necessity of dividing the C, which says how much the energy changes per temperature. We need to divide that by C again. And so this is the origin of this division, C over T. And when you put in the data, the C 10 to the minus 9 joule per Kelvin, and you look at this KBT, which is at room temperature 26 millielectron volts, and reduce it to joule and so on, you obtain a thermal fluctuation of 36 millikelvin. So the temperature of this little pixel isn't defined to better than 36 millikelvin. And now please cross out this last line, which I don't understand anymore. I don't know what went through my head when I wrote that. It's insane somehow. So the thermal fluctuation of the temperature of this object is 36 millikelvin. It's more than what comes in by the thermal radiation. So the 10 to the minus 9 watt are definitely too small to be detected. We need 3.6 times as much to be out of the noise, because 3.6 times 10 to the minus 9 watt will produce 36 millikelvin of real signal. And that will be just coming out of, or that this will correspond to a signal to noise ratio in the thermal noise of 1. And to measure that signal electrically will be no problem because the electrical signal to noise is 100. So anything above 3.6 times 10 to the minus 9 watt might have a decent chance of being measured. And that corresponds to a temperature of an object out there. So yeah, complicated calculation, but it gives you immediately some limits, some limitations of your sensors. Yeah, so here is another structure that was produced by the Korean Advanced Institute of Science and Technology in '99. They said, okay, these bolometers of Honeywell, we can do better. Now, if we go back to the structure of Honeywell, there's a lot of unused space. So for instance, these arms, whatever radiation impinges here is not used. Then the gaps are not used either. So they said, okay, instead of having some structure like this with a lot of unused space, let's put a second level of a continuous absorber on top. And that will absorb the energy, then will heat up the structure, and then we can make a resistive measurement. So they had a titanium 50 by 50 micrometer, also pixels with silicon oxynitride membranes, titanium resistor with 5 kilo ohm. They say a relatively high temperature coefficient of resistance, but I'm pretty sure it's around 0.3, maybe 0.4% per Kelvin. Certainly not like a vanadium oxide. And the fill factor, they say, is 92%. So of course there is a little gap to the next pixel, which is unused, but from the area that this sensor covers, 92% are covered by absorbing material. And then you see here some thermal conductance in air, 4.3 times 10 to the minus 5 watt per Kelvin, and in vacuum, 6.3 times 10 to the minus 7, a factor of 100 better. There you see how important eliminating the conduction by air is. Air removes 99 or something close to 99% of the heat because of the small distances. And the remaining 1% is maybe, well, the conduction by the material, solid materials and by radiation. And so they obtained a responsivity of 1,600 volts per watt. Now, I don't know how those volts are calculated because it's a resistive structure. So they need to power that with some current and then they can obtain some volts. And then there is a detectivity that is fairly high. That must be said. Then we have some alternative structures from the Middle East Technical University again. So that's again Professor Tayfun Akin. They made some bridge type sensors with some absorbers. The fill factor is of course very low, 44%. There's 56% of radiation that doesn't get absorbed where it is useful. And well, the temperature measurement here is done with a diode, if I remember well. Did I write that here? CMOS N-well readout using diode. Yes. A diode is also, well, you know about diodes. Proportional to absolute temperature measuring sensors. Diodes are excellent temperature measuring devices, and so this is what is integrated here. And well, one can calculate an effective TCR of that diode response to be 0.26% per Kelvin. So okay, not so good, but okay. And the pixels are 80 by 80 micron square, so they produce large arrays of many such sensors. All right. Now, let me talk about thermal pressure sensors. Start talking about those. We have here one of the earliest structures that I investigated while I was still a postdoc. I'm still, proud of that, because we had these sensors that were used for all kinds of things, and then I said, okay, let's try whether we can make a pressure measurement with those. So you have two opposite cantilevers here, and so one of them is heated. So some heat power is dissipated right here in this resistor. Some P heat is dissipated by some current flowing through here and out here. And that increased temperature will cause heat flow from this structure to the other structure by the conduction through air, if there is air. So as a response to that temperature increase, the delta T, let's say delta T1, via this heat conduction, this structure gets heated up to some delta T2. And that delta T2 depends on the pressure of the gas. Because if there is vacuum, there will be very little heat transfer. Well, by irradiation, of course, still a bit. But if the pressure of the gas is high, of course, there will be a lot of heat transfer, and then the delta T will be large. And then you can measure that delta T with respect to the T0 of the chip by integrated thermopiles. So this was the setup, and when I was a postdoc, I had this job of taking over some work from some other guy. I then had to build up a cryostat, a machine that can be evacuated, where temperatures can be changed from minus liquid nitrogen to 150 degrees. And so I could switch, I was able to determine the pressure in this chamber and then vary that pressure. And this turned out to be a superb pressure sensor. And you could just heat up the structure with a given current, and then you got out a signal V that depended, a thermoelectric signal that depended on the pressure, kind of for free. So that was the starting, and then I thought, oh, micro sensors can be pressure sensors. And that was in the first year of my postdoc, and then my brain started working, and now I'll show you some ideas that I had. But anyway, what we need is always, we would like to measure the thermal conductance of the gas, via the pressure-dependent gas conduction. So we need a heat source somewhere, and then we need some temperature measurement. And that can be thermoelectric, thermocoupled pairs, or thermally sensitive resistors. And the implementation of the structure can rely on membranes, on diaphragms, on cantilevers like here, on bridges that cross some micromachined cavity. They can be produced using front or rear micromachining, bulk or surface micromachining. You can invent them, and I'll show you some example of a surface micromachined pressure sensor. This was my first application of sacrificial aluminum etching. Think of chapter 2, where we talked about that. So here is a CMOS structure that mimics a classical pressure sensor for low pressures. This is called a Pirani sensor, not because it measures the presence of piranhas or something in the river, in the Amazonas. No, it was Signore Pirani, Italian, who invented that sensor. And the sensor is easy. You have a heating wire in the center of a cylinder. The cylinder is connected to some support and has temperature T0. The heating wire is connected, to electrical connections, and which ultimately are also connected to the same physical structure in which this whole sensor is mounted. So there is T0 also down here, yeah, and then if a current is sent through that wire, of course it will heat up by resistive heating, ohmic heating. And the heat that it dissipates will be invested in increasing its temperature. But then it will lose power by the conduction through the gas. So there are two channels for this wire to lose its energy, dissipated thermally in its material. One is by conduction through the gas, and the other is by conduction through the supports that have to hold it in place. So there is an overall, I should say, there is an overall thermal conductance, the thermal conductance by the gas, TH, gas, which depends on the pressure. And then we have the thermal conductance by the supports, which will not depend on the pressure of the gas. And those two together will make the total thermal conductance of that structure, the thermal conductance between the wire and its surrounding. And if I write this down in the way in which you have seen it before, delta T times G thermal total pressure sensitive must be equal to the power that is dissipated electrically in the wire. And this is, of course, its resistance multiplied by I square, or the applied voltage divided by R. So power is dissipated, and then this power leads to a temperature increase of the wire that depends on pressure, because the thermal conductance separating the wire from its environment changes with pressure. So now what happens? If there is no gas, that conduction of gas will be very small. Therefore, the wire will heat up a lot. So at low pressure, we'll have a strongly heated wire, and at high pressure, we'll have a weakly heated wire. Or if we want to keep the temperature of the wire constant, it just means that at lower pressure, we have to dissipate less heat to reach that temperature increase. And at higher pressures, we'll need to heat it up more to compensate for the better conduction of the gas. And so how to transform this structure into a microsensor? Because the dimension of this sensor is, well, let's say typically centimeter, if maybe 5 millimeter, 1 centimeter, something like that. And how to transform that into something that has only a dimension of 200 micrometers, like here? It's by making it flat. So what you see here is a schematic cross-section of an air gap over which there is some structure, some planar structure made of dielectric materials of the CMOS process. This is the passivation. This is the intermetal dielectric. This is the contact oxide. And this is the field oxide. And this used to be metal 1. This is gone because it's sacrificially removed by the sale process. And then we have the second metal in this process, which allows us to integrate some structures between the IMD and the passivation. And what you see here is a meander of this second metallization. It's actually metal 2, this M2, metal 2 is equal to aluminum, some aluminum alloy. And I designed it as a meander in order to have something like 100 ohm of resistance between this contact and this point. And that meander is fully protected within dielectric layers. So it's really packed, encapsulated. And if I do a cross section across this structure, you will see, many little cross sections through that line. This is symbolized by these cross sections through the line. And then at this point, I follow the line to go from the meander out towards the external side. And then for sure, there will be some contact pad, yeah, to do some measurement with the bond wire out there. Yeah, and the same here. Yeah, so there's another bond wire to do the measurement, hook it up to some instrumentation. Yeah. Now, what about this gap? This gap is produced through little openings that were cut through the passivation and through the intermetal dielectric. And there was also metal 2 up here. And this has been exposed to the sacrificial etchant, that removed the metal 1. So there used to be, this used all to be full with metal 1 and metal 2. Yeah? It's all gone. Yeah? Through these holes, yeah, under this plate of structure that is a little like a drum structure, yeah, suspended on the side, yeah, but under etched from the side right under its whole extension. Do you see that? What? Yeah, this whole plate, this whole circular plate, yeah, is held in place at these points, yeah, along these line segments, yeah. So it's really fixed there. Now the passivation just makes a little jump because there was metal underneath. So yeah, of course there's some topography, but the metal was removed. Yeah, so this is the outline of the metal that was removed, and here are the opening windows that allowed us to reach that metal, to remove that metal. Yeah? And you see that we have a distance to remove metal of 100 micrometers horizontally. Now, when you go back to chapter 2, 100 micrometer of sacrificial aluminum etching is not so much. It's easily done with the commercial etchant that we used. So all we had to do was to design that structure, kind of unconventional design. A circuit designer would say, what kind of a funny structure? That can't be a circuit. Yes, indeed, it's not a circuit, it's a sensor. And it becomes a thermal sensor because now this top structure is separated from the underlying substrate at temperature T0 by some insulating gap. So if I generate now here in these meanders some heat power, yeah, this electrical power, if I dissipate the electrical power here, the power has to flow away via the solid. This is the power that goes via the support. This is equal to G thermal support times delta T. And then there is this component that goes through the gap. This is the G thermal. So let me write that here. G thermal gas as a function of P times delta T. So the temperature will be gas dependent, like in the classical Pirani sensor, depending on pressure dependent. And if I want to keep the delta T here constant, then I need to heat up as a function of pressure in some system. And this is something which I will discuss then tomorrow with you, how to do that and how to integrate that into a system. And yeah, so that will be tomorrow's program, and the rest of the chapter will follow as well. Yeah, so thank you very much for your attention, and apologize for talking a few minutes longer, 5 minutes longer, taking into account the fact that I started 5 minutes late because of this program problem, yeah, that I need to solve. It's not yet fully solved. So thank you, and see you tomorrow then.